Okay, today we're going to talk, or at least introduce you to EES, Engineering Equation Solver. But a couple quick thoughts. We're going to get into some harder stuff. It's not like harder calculus or harder math or harder equations, but we're going to give you some tasks to do that aren't exactly. We're not going to hold your hand, right? So we'll say, hey, figure this out, right? And you're going to have to just figure it out. We're here to help, and during lab, you've got some really good essays who've all done this before, and they'll help you figure it out. But we're not going to hold your hand, and it's very possible that you leave lab just a little bit frustrated, right? And we want it to be that way. Not because we're mean or sadistic or anything like that. It's just that we want you to go through the process, the struggling to figure it out, right? That's what engineers do. Engineers figure out problems. They solve problems. If there was some step-by-step cookbook way to solve this problem, well, why would someone pay you to be an engineer, right? There's already step-by-step things. Your job is to figure it out. Your job is to create the step-by-step process, right? So it's different than perhaps some lab classes you've done in high school or even stuff we've done in here. It's going to become less step-by-step and more figured out, all right? So we're here to help. We want you to learn, but learning is not always easy. It's not always comfy. It's not always hand-holdy, right? Learning sometimes is tough and sometimes it's frustrating, but we're here to help you learn, all right? We're not here to teach you. We're here to help you learn. So just be aware of that. All right. Next up, we're going to talk about Engineering Equation Solver, EES. EES is pronounced EES. You can download it and install it on your own machine if you have a Windows machine or Parallels or something like that. But it's easiest just to run it remotely using Citrix or XenApp here. Secondly, I'm going to switch this over to laser pointer here. Secondly, what it does, it solves a big set of nonlinear equations, right? So you can give it parabolas and hyperbolas and property plots and what other kind of stuff, equations of state for different fluids and stuff. It's designed originally for like the thermal fluids, refrigeration, heat transfer stuff, but it works really for anything. And it's getting more and more broad. It uses equations rather than assignments, right? In an assignment, you say x equals 7. And you're saying, hey, there's this variable x, and here's what it is, 7. Whereas an equation is saying, hey, there's some relationship, and the x might be on the right, the x might be on the left, there might be 3 variables in there. So it's really an equation solver. And then what it does, you'll give it a guess value. So you say, I think x is -1, and then it'll kind of hunt around and try to find a set of values that solve or that satisfy all the equations. So it's an equation solver, not a programming language, right? A lot of people get frustrated because, well, this isn't a programming. No, it's not a programming language. It's not meant to be a programming language. It's meant to be an equation solver. Some things you will surely hear about EES, especially from people outside mechanical engineering, that it's a black box, right? And that's a little bit true. But the numerics behind it are really, really complicated. But it's all available. If you dig through the support documentation, it's all there, right? And then one of my favorites is nobody outside of UW uses EES, right? I would say that's true that not enough people outside the UW use EES, right? But to say nobody outside of UW uses EES is just not true. If the authors of EES, both of whom I know well, right? And I'm not trying to pitch it, right? I am trying to pitch it, but this isn't like a money grub. It's an amazing tool. I happen to know the authors well, and neither of them, they're both amazing researchers. Neither of them are amazing marketing people. They're not businessmen per se. So it's not marketed as well as it could be, right? There's General Electric. You may have heard of General Electric. They use EES. And then who else uses EES here? There's Ford, right? Okay, and SpaceX has a few EES licenses. Boeing, they might be a competitor. They buy a lot of GE stuff, but they may be a competitor to SpaceX. Oh, and Carrier, you look on the roof of any building, and there's probably some Carrier equipment up there. Trane, if it's not Carrier equipment, it's probably Trane equipment. And then Modine, that's a big refrigeration company. Oh yeah, NASA, you may have heard of them. Is that a competitor or a customer of SpaceX? Hard to say. NIST, National Institute of Standards and Technology, or Standards and Testing, and then NREL is the National Renewable Energy Lab, NOAA, National Oceanic and Atmospheric Administration. All right, EES is an amazing tool. And most people, when they first see it, they're like, what is this? And then shortly thereafter, they're like, well, I'll just do that in EES. Right? It's really pretty cool. Where are you going to use it? Lots, right? You'll do computer programming in 301, but the first place where you'll really see the amazing features of EES and thermodynamics. And then heat transfer, energy lab. Oh yeah, you can use it in statics. It'll actually save you a lot of time in statics. Mechanics and materials, because there's systems of equations you have to use there. Your senior design, design machine elements, right? Machine component design, you'll use EES a lot there. Okay, so hopefully this slide is over by now. Yeah, okay. So let's just say we have a set of equations, right? Equation 1, 2, and 3. Equation 1, nice linear equation, makes a diagonal line. Equation 2, another one, but in a different plane, another nice diagonal line. And then here's this one that's parabolic in x and z, right? So, you'd be hard-pressed to write a MATLAB program or a Java program or a Python program, C++ or C++, to do that, right? But that's where EES comes in. Right, so you can solve it by hand, right? You solve this one for y, and you get y equals 3 minus x. Then you just plug this y back into here, and then you get this. Then you can solve that one for z to get z by itself, and then you put z back up into this one, and then now you just have x's, and this is a quadratic equation that you can solve. You rearrange this like this, and then you can do this. You get these two values for x. Once you have the two values for x, you can figure out what the values for z must be, and then you can go back and get y, right? So that's one way to do it. Alternatively, you can just punch these into EES, right? Just type in the three equations, right? 1, 2, 3, type them in just as they are, and then you hit solve, and then you'll get the solution, all right? And I've made some videos that show you how that works for this exact system of equations. Some key things, you can enter them in any order, right? So just because you know what z is doesn't mean z has to go first. It isn't an assignment, right? The equations can go in any order. Now there's some better practices, but they can go in any order. And then EES will make sure that, hey, if you've got 3 unknowns, you better have 3 equations, right? And if you have 4 equations, you better have 4 unknowns, otherwise it's overspecified or overconstrained. So this is what it would look like. There's an equations window. I'm going to go through this quickly because I'm going to actually go through and do this in the videos too. So we get different values of x, y, and z. Right? You get you just punch this in and solve it, and you get 2.7, 0.29, and 4.29. Right? And you can get these 3 things here, right? But back here we said that this is parabolic. Right, and that means we actually get 2 values of x, right? But EES, maybe EES isn't as good as I thought. EES only gives us one of them, right? And it completely neglected this other, right? And that's because the way EES works behind the scenes. What EES does is it makes a guess, and here you can see the guess is 1. And then it uses Newton's method, which you probably might have done in calculus already, maybe not, where you make a guess, you evaluate, you find the slope of the curve at that line, you shoot that line back down to the x-axis, and then that's your second guess, right? And you keep doing that until you get somewhere close to the intercept. So if you guess wrong, or not wrong, if you just make a guess of 1, it's going to find the solution that's closest to 1, right? Whereas if I pick -1, I changed my guess value to -1, it'll find this different one, right? But there's a big difference here, right? Here, with this value of x, the values of y and z are totally different. If I pick -1 as my guess value, I get a different value of x, and then different values of y and z, right? EES doesn't know what you're looking for. If you're looking for, say, like a velocity or a pressure or a temperature or something like that, that has to be positive, this makes sense. Right? If you're trying to find out how much money you lost in the stock market, right? Well, then it's some negative number, so you have to guess a negative number, right? EES does not know what you're looking for. EES just finds a certain set. So these guess values and then upper and lower limits, right, are really, really important once we have real application problems. We'll talk about that more in the examples. Next up, comments. Right? And we've talked about this a little bit. You should always put comments in your code. With EES, there's 3 ways to do it. Put it in quotes. That's what I usually do. You can put it in curly brackets. Right? That's another way to do it. And it has advantages and disadvantages. And then double backslash. Or double, is that a forward slash? Forward slash. Double forward slash will also make things a comment. Right? And you should always comment your code. And I'm calling this code, it's really, you should always comment your sets of equations because it's not really computer programming code. So that when you come back to this next week or next month or next year and you need to say, what was I doing here? That code is critical in helping you figure that out. All right. There's also what's called a formatted equation window. This thing here, this is a little hard to read. Right? Admittedly, this is hard to read. It's like, what is that? But if you put it in a formatted form, it's like, oh, okay, this is a lot easier to read for those of us who are used to looking at equations. And this is ugly, right? So this is a very useful tool called Formatted Equations Window. This is the equations window, formatted equations. Secondly, you will probably do problems that have literally hundreds of equations and hundreds of variables. Sometimes maybe all I want to know is f. Right? I don't know what f is here. What is this here? Looks like it's something to do with the Reynolds number and friction factors. So all I want to know is f, so I right-click on f and I say, hey, this is a key variable. This is one of the key things I'm trying to find. Right? I don't necessarily care what the diameter of the pipe was or what these constants are. I just want to know what f is. So I say f is a key variable, and then there's a second window here in the solution window. There's the main one that has all the solutions, and then the key variables, which just lists the one that I'm most interested in. All right. You know, we always say, oh, my favorite thing, and I might say this like 6 or 7 times with EES, but my really favorite thing is the fact that EES manages units very well. Right? In the engineering profession, we're trying to do things in the real world, right? And these things often have units, right? Units of length, or units of mass, or units of speed, or units of velocity, or units of whatever. And so EES helps you keep track of that, right? So it doesn't change the units for you, but what it will do is say, hey, you've got feet on one side of the equation and meters on the other, or in this particular situation, kilometers on one side of the equation and miles on the other, right? And if you don't get kilometers and miles straight, you'll instead of this satellite coming down through here and then just slipping into a nice orbit like this, right? It comes cruising in like this and then slams into the Mars surface, right? So this was actually a unit mistake. I think it was between the researchers at Caltech or JPL. Caltech and JPL are kind of the Jet Propulsion Laboratory, NASA, also a EES customer. And then the people in Houston were not using the same unit system. And then so that caused this crash. So don't do that. Speaking of units, for instance, maybe you're using a sheet of paper and you're trying to do some calculation with a sheet of paper. It comes in inches. We know here in the United States it's 8.5 by 11, right? But it works a lot better if we convert stupid units like inches into more reasonable units like meters, right? And you do that with this little command here. I say, well, the width is 12 inches times some conversion factor, right? Why is this times? Because to convert from inches to meters, it's just some factor, right? In fact, it's 1 over 39, right? So I start with 12 inches and I multiply this by 1 over 39, 1 over 39. and that gives me some value, right? So what actually happens is that it'll multiply the 12 by 0.0254, which is 1 over 39, and or 1 over 7. No, yeah, 1 over 39. So that's what actually happens. You're multiplying your inch value times a conversion to get meters. All right, and EES will do that for you. In fact, you're going to do it this week. And then what you can do, there's a button that allows you to check your units, where I said, okay, let's see, width is inches, but I'm going to convert that to meters, right? So the width is in meters. And then the height is inches, but I'm going to convert that to meters, so that works out to be in meters. And then the area, consequently, is width times height, right? But if I look at here, I didn't apply a unit to this. So EES says, hey, Dress, slow down, man. Your height is in meters, your width is in meters, and if you multiply it, now EES doesn't know what A is, right? EES doesn't know what this equation means, but what EES does know is that you're multiplying meters times meters. So if this is meters times meters, this had better be meters squared, right? The equations have to be self-consistent, right? The same units on both sides. So it says, hey, you click the button, it says, hey, we detected a problem. And so you have to say, oh, that's right, area should be meters squared. So then you add the correct units to that. And then it says, hey, no problem, you're all good. Right? So this is our strongly suggested way to deal with units. Right? The United States is slowly moving over towards using the SI system. There's a bit of irony here. I don't know if this is a political thing or not. I don't think it's political. We're not supposed to say anything political in the classroom, and with good reason. But this might be considered political. That here in the United States, we're a country that prides itself on liberty. Right? Prides itself on doing things our own way and saying, no, we can do better. The freedom of choice and freedom of everything else, and all these freedoms we have, which are amazing, and we're really lucky to have these freedoms. I mean, you talk to some students from other places around the world, and they do not have the freedoms that we as American citizens have, or at least for those of you who are American citizens. We're very, very lucky. But what's ironic about that is that we still use a unit system that was handed to us by the British. Right? And we so proudly celebrate the fact that we said, hey, British, we're declaring ourselves independent, right? And we have this big party every 4th of July, but then we still use their units, right? Everywhere else in the world, including Great Britain, has said, these units are kind of dumb. Feet and pounds and inches and, all these bizarre units, slugs. The rest of the world has switched over to SI units, so we strongly recommend that you also use SI units, right? The big auto manufacturers, the airline manufacturers are all largely switching over to SI units now. The HVAC companies, Train and Carrier, still do a lot of stuff in English units. I don't know why. They're just a little slow to change, I guess. But anyway, we're going to strongly recommend that you do all your work in SI units. And the pre-lab and lab will require you to deal with that a little bit. All right, so in general, right, the base units are kilograms, meters. Oh, I got to switch over to laser pointer here. Laser pointer. Kilograms, meters, seconds. Newton is a force. Kelvin is a temperature, right, and so on. There's all these, right? So what is density? Density should always be in kilograms per meter cubed, right? Area, meters squared. Square inches, square feet, hectares, acres? No. Just use square meters. Acceleration, meters per second squared. Start with these, mass, length, time, and all your derived units, right, should be in these three things here, right? So power is a watt, which is a joule per second, which is a Newton meter per second, right? Newton meter per second. So if you have a problem that's given in inches and feet and slugs and everything else, convert it into SI units right away. Do the problem in SI, right? And then when you're done, if you need to give something back in feet or whatever, you can display that as a secondary unit. You'll come up with a solution in newtons, but then you can also display it in pounds, or pound is force. All right. So here's a simple example. We have another video for this, but I'm just trying to figure out what the pressure drop is as water flows through this little pipe elbow here, right? And so I know the density of water, right? Most of you know this from chemistry, is 1 gram per centimeter cubed. Not a great unit. What would I rather have? I'd rather have kilograms per meters cubed, so I'll have to convert that. Velocity is through 12 feet per second. Now that's unfortunate. The seconds are okay, but I got to get rid of that. And then bend loss coefficient 0.3, right? And that's a dimensionless value. So it turns out you'll learn in fluid mechanics, ME 363, that the pressure drop is some coefficient, right? This K here, times the density times the velocity squared divided by 2, right? The units on this turn out to be pressure. If you do it all in SI units, this turns out to be pascals, right? Newton per meter squared. Is it Newton per meter squared? Yeah, Newton per meter squared. If you do it in English units, you get some number, but then that number has to get converted to some other unit. That like pounds per square inch, which would be kind of a hassle to do. It's not self-consistent, and very frequently we're given mixed units, right? Not fundamental SI units. So this is a pretty real-world problem, right? So what we're going to do is enter our known values, right? Density, rho, that's the Greek letter rho, is 1 gram per centimeter cubed, but I'm going to multiply that by the conversion factor. I'm going to convert from grams per centimeter cubed to a more fundamental unit, kilograms per meter cubed, right? So grams, centimeters, kilograms, meters. And then the velocity, right? I'm just going to convert that from feet per second, into something more useful. I'm going to convert the feet per second to meters per second. And since the coefficient is dimensionless, right? We just leave that as dimensionless. And then I can just punch this stuff in, right? And then I'll get some delta P, and delta P will wind up looking like this, delta P. And it turns out to be 2007, right? And so I could right-click on this and then also display it back in the original PSI, which is what a lot of HVAC engineers, plumbing engineers, what they want, all right? So that's an example of how you do that, and we'll do that in a video too. There are some constants, for instance, pi, gravitational constant. There's a bunch of stuff in here that are pretty common. Gas constant, we use that quite a bit, but I use pi really most of all. That's the most common one I use. So you just write pi hashtag, pi pound, and that'll give you 3.14159628, whatever. Okay, so that's that. Now, this is a classic mistake. Classic mistake. To convert temperatures, the problem with temperatures, it's not just a scale factor. Problems with temperatures are that they have different reference values, right? 0C is not the same as 0K, which is not the same as 0F, which is not the same as 0R. So they have different 0 points, right? So it's not as simple as just multiplying by something. So we use a different function. We use convert temp, and we say what I give it in, and then, so I want to convert from Celsius to Kelvin 10, right, or 10C. I'm going to convert this to Kelvin, and we know that it's 283, so 10C is 283. This, right, would give you something wrong, right? This is saying I'm going to take 10 degrees Celsius and multiply it by another temperature, right? This doesn't work because this is a temperature. This would be Kelvin. I'm converting from C to K, so this would be a temperature in Kelvin. So I'm multiplying a Celsius by Kelvin. What the heck is that? That doesn't make any sense. It is also not this, right? This doesn't make sense because you'll get temperature squared, right? And that just doesn't make any sense. This one does make sense, right? If I have a difference in temperature, right? Say it was 5 degrees C when I woke up this morning, and now it's 15 degrees C, right? The difference in temperature was 15 C, or was 10 C. Right? It went from 5 to 15 from the time I got up this morning until now. So if I converted that from Celsius to Kelvin, what's the conversion from Celsius to Kelvin? It's just 1. 1 degree Celsius is the same, size as 1 degree Kelvin. So this conversion factor would be just 1, but I would get, I'd still get just 10, right? Which is not the 283 that I'm after. So there will be some problems where you have to do this week. So just be aware that converting temperatures is not a multiplication. All right. Okay. Finally, printing. I can tell I did this at home with my old printer. So we will we're going to always ask for you for PDFs. So what did I write here? So don't turn in a screenshot and then paste that into a Word document or something like that. Enable Kumo, right? And I went through this with another video, so you can see this. But I'm going to go through this pretty quickly. So you're going to run EES via Citrix here, right? And then you're going to print this as a PDF, and you're going to store this PDF here in the cloud. And then, when you're using your computer to access Canvas, you can also access the cloud here, and then so you can go from here right to Canvas. Right, so using Kumo and then Box Drive or Google Drive is certainly the easiest way that you can run software on one computer, store it somewhere else, and then access it from your computer. It's a really, really good way to go. So please do that. I think most of you have been pretty good about doing that already. So you'll use whatever the machines are at 1410 eHall or 1410 Engineering Drive are using. It's either Microsoft PDF Writer or Microsoft Print to PDF or Qt PDF Writer. And so you'll choose this printer, and then you'll print it, right? Whatever you want to print, equations, formatted equations, solutions, key variables, whatever. And then when it's going to save, so you're saving it as a PDF. Right, so where does that file go? You have to specify somewhere that makes sense. Don't save it on the desktop of a machine that's in a building you don't have access to. Right, save that PDF somewhere that you can access. Save that in Box. All right, and then you'll save that, and that's it. Okay. Now, speaking of cloud storage. Every one of you, like at some point, will have a hard drive failure, or you'll leave your computer on top of your car, or you'll drop it off your friend's deck, or somebody chucks it out your dorm window. Who knows? Back up your data, right? And the best way to back your data up is to put it in the cloud somewhere, right? Either a network access drive locally, or the cloud, Google or Box, or something like that. All right. And I'll finish up with this little statement here. There are two types of people in the world, those who back up their data and those who will, right? I used to be one of the people that didn't back up their data, and I lost literally years of work because I was lazy and sloppy. Is a very, very painful experience. So please, please, please keep your data somewhere safe that's backed up, not just on the hard drive of your computer. That's it. I will see you guys soon.